Good morning, everyone. Welcome back again. Sorry, it's been a long time since my last video. I was first away to Joburg, and then the second one. What was the second one? But yeah, I had a busy 2 weeks, and now I'm back. So today I want to talk about neutron stars. So neutron stars are incredible objects. They are space objects, so we are back in space, yes. um, in my first video, I talked about black holes. Now, effectively, a neutron star is the stage before a black hole. Most stars will end in a neutron star, and that's that. The only way to go from a neutron star to a black hole is gaining more mass or being a massive neutron star when first formed, then it will collapse under gravity to form a black hole. So these are the stage just before it. They are useful objects. Now, it starts like you have your star being born, it goes through its lifetime. If it's a big enough star, it will create a supernova where the core collapses to a single iron core effectively while the rest of the star explodes in a supernova. But then that core, that is a neutron star. Now, a neutron star has a second name. Maybe most people know it on the second name, named a pulsar, which is a neutron star that, due to angular momentum of the big star collapsing like a figure skate, starting to spin very fast. The neutron star is spinning very fast, and because of massive magnetic radiation, also due to conservation of magnetic fields, you it's it has a massive load of magnetic field strength stuff seen nowhere on Earth, close to something like that. And then it guides, these magnetic field guides electrons in the inside out to the poles of the star, and it gets blasted into two jets. So as the neutron stars spin, it creates these two light beams effectively spinning around and around, which we can then detect as pulses going. And some of them spin very fast. They are millisecond pulsars, so every few milliseconds. Others can are a bit longer with few seconds. But yeah, so this thing that's about the size of New York. Most of them are not even the entire New York, Manhattan, just the island of Manhattan, about 10-kilometer radius. Uh, they turn that big thing every few milliseconds. That's how fast it's spinning. It's really incredible objects that. But what makes them more impressive, and it was important in the discovery that were last year made, was these neutron stars. So when they collapse, they are mostly iron. There are other stuff, but mostly iron. And they are so dense, compacted, and gravity keeps compressing them. So the forces between neutrons being forced to go into each other, that's what's keeping the star in its shape. So it's not a nuclear fusion anymore as done in the sun, but a two neutrons has been forced into one another. And I mean, if you stand next to someone else in a room, you put another person in the room, another person later, no one will move, but no one can fit in anymore because there's no more space. So that's how the neutron star keeps his form. So between massive angular momentum for spinning, massive magnetic fields, these neutron degeneracies where they are totally filled, they still give off radiation, and that's the important part. Now, a black hole is amazing stuff. They are the vacuumers of the of the universe, but they don't give off radiation except for the jets that are pressure being formed on the surface of the black hole, not inside a black hole. Because if it's past the event horizon, it's done. But these ones do give off electromagnetic radiation, which is light, which we can detect and see. But it's since it's very small, it's very hard to find them, except if they have these pulses, because the pulses are a beam of light, effectively. But this is still important. Now, in 2015, when the merger of the two black holes occurred, it was a big story. Gravitational waves were confirmed. Einstein's theory of relativity was confirmed once more. It was a big deal. But we couldn't actually see it happen. We could detect the gravitational waves and we could pinpoint it somewhere in that direction, but we can't see it. Now, the only other stuff that might have, it was though theorized, might have enough to actually be detected is the merge of two neutron stars. They are, since are also so much compacted, I mean, if you were to take a teaspoon of neutron star and you put it on a scale next to that weight scales where you put one side and other side. If you were to put the neutron star on the one side and a cruise ship, massive cruise ship, the passenger ships, a massive ship compared to a teaspoon of neutron star, it will still do this. The neutron star, one teaspoon is about 2 billion tons, metric tons. So it's quite impressive. Or is it two? It's 2 billion. Yeah, million. No, I'm not sure. but yeah, it's still a massive load, which would then, in all cases, the neutron star, even if it's just this tiny bit, would be heavier than a passenger cruise ship. That's just so being so compact, so heavy. They also bend space-time, just like the black hole. Although the black hole is much stronger and bends space-time more than a neutron star, they can still bend space-time. White dwarf can also do it, but he's even more less effective. Everything can actually bend space-time. It's just the efficiency. Even you can bend space-time. So yeah, but I mean, you don't weigh more than a passenger cruise ship. So these ones bend space-time heavy, and that's why when they merge, they also create gravitational waves. But what is important to know, since they do have electromagnetic radiation, even if it's dim, since it's small, they still have it. And that's where the moment they merge, became one neutron star, or maybe be enough mass to collapse into a black hole, they send out a blast of radiation. And this is where all of the theories of multi-messenger astronomy was confirmed. So it was theorized that every single thing from the merger would have the gravitational waves, the explosion would have high energy radiation, all the way down to low radiation. And gravitational waves, we have seen them, electromagnetic or radiation from explosions, we have seen them, we have confirmed both, but never have we had them together, because the ones that had electromagnetic radiation is not strong enough to compare to make viable gravitational waves, while the what's the word? While the ones that have the enough mass to bend space-time enough to actually detect the gravitational waves they don't emit night black holes. So this one is right there in the middle. Not is a bit more to the black hole side, but it has both. So when the merger went, the gravitational waves got made and it was sent out, and we there were three active detectors at that stage. Two of them detected it, the other one did not. Using this, they knew they can triangulate. So since this one could see, this one could see, and this one not, we know it had to be in that direction. And then exactly 1.7 seconds, as predicted by physics, we picked up the first high energy radiation from the explosion. Now, so it's merger, so no radiation, explosion. The first ones to get released is the high energy radiation, and then as it cools down, the others are released in lower energy. So you would expect your high energy to get first, and then all the others later. So all of these ones, 1.7 seconds later, Fermi detected it, the space telescope. So using Fermi, his location at that point, and the two detectors on the ground for gravitational waves, they could say, okay, since they overlap with this one, it should be in that. So they already made it smaller, and then came HES. It's an important one for South Africa. South Africa and Namibia is very much in charge with HES. They are not the only contributors. I think most of the money don't even come from us, but we run a lot of it. Poch does a lot of work with HES. They were the first one to look in a certain, and okay, there we see high energy radiation from that point. So we had we were the first to actually pinpoint it. Well, HES were, but we can have a bit fun saying it was us. And then as the lower energies got released due to the explosion being cooling down, the others started coming through X-ray, uh, light waves, infrared, radio. And then came another news, Sol telescope that's in Sutherland were the first to correctly confirmed that it was a kilonova. So you will hear nova. So the supernova is just a normal explosion. It's star dying, go out. But in a kilonova, it's already a dead star. Both of them are dead stars. So when they collided and made this explosion, it was new elements that were created that weren't previously there. And in most of these cases, it's gold and platinum. I know my one lecturer told me, it's like, if you want to be rich, just go there. There are so many gold at this stage, you'll have more gold than that can fit on the earth, which were created. And Sutherland salt were the first ones to correctly identify. This is also the first ever kilonova we have detected. So another theory confirmed. So a few theories confirmed with just one merger. That's why it's important to study the stuff. We had the idea of how it's going to work. We needed confirmation. Now we have confirmation. Now we can try to run models, see how we can improve on our models since we have a thing to work off. And then one day maybe the engineers will figure out, using these knowledge we have built up, how to make stuff that's using that to make the earth a better place. Maybe they figure out how to work with gravity, because that thing has gravity, and it showed us how it works with the electromagnetic radiation. Well, all of them have gravity, but intense gravity. So yeah, if you like this video, hit the subscribe button and the like button, and see you next time. Thank you.